Today we will study merge sort. Merge sort runs in theta of n log n time. So it's faster than insertion sort. What is merge sort? Merge sort is a sorting algorithm using merge. As you know, insertion sort uses insertion to sort, but merge sort uses merge. Then what is merge? Given two sorted lists of keys, generates a sorted list of the keys in the given sorted list. For example, look at this blue list and red list. We are given two sorted lists. And then the result is a single merged sorted list. What is the input of insertion? Do you remember the input of insertion? Park Jong-hoon. The input of insertion. I can't hear you. Speak up. A list of numbers plus a new key. One key and a list of keys. And the list should be sorted. Okay? A sorted list and a new key. Putting the new key in the sorted list is insertion. In this case, we are given two sorted lists. Okay? So that's the difference. And let me show you a merging example. Okay? We have two lists. They are sorted. And then first, we compare the first two elements and take the smaller one. Okay? Which is smaller? One is smaller. Then move it to the resulting array. Then we do the same thing in the remaining lists. In this case, they are 2 and 5. This time, 2 is smaller, so we move 2 to the output array. Okay? And 2 is removed. Next, we compare 4 and 5. 4 is smaller, and it is moved. In this way, we can merge two sorted lists. Then let's check out the running time of merge. Let N1 and N2 denote the length of two sorted lists. Then its running time is theta of N1 plus N2. Let me show you why. Let's count the number of main operations. There are two main operations. One is comparison and the other is movement. Okay? Two operations. And one important thing is the number of comparisons is less than or equal to the number of movement. Why? 박근배, can you explain why? 김범진.
key has some time.
최소리.
No, worst case we have to compare and process time.
But I'm asking you why the number of comparisons is at most the number of movements.
And the best in the best case we have to process.
Okay, that's not bad, but simple explanation can be like this. Every comparison is followed by a movement. Okay? If we compare two keys, then one of them should be moved. So, this inequality satisfies. And obviously, the number of movements is n1 plus n2. It's quite straightforward because we have to move every key from the input list to the output list. And because of this inequality, we can get this one. So, it's like this. Finally, the running time of merge is theta of n1 plus n2. Okay. Now it's time to explain merge sort. Merge sort is a divide and conquer approach. It has 3 steps: divide, conquer, and combine. First, we divide the input keys into 2 lists of half-sized keys. And then sort each list recursively using merge sort. And finally, we merge the 2 sorted lists. Okay, remember these 3 steps: divide, conquer, and combine. Okay, let me show you an example. What is the first thing to do? Divide, yes. So we divide this array into 2 half-sized lists. Divide. And what's the next step? What? Divide? Yeah, right. But the next step is perform recursive merge sort on this array and this array. Okay? Then the first step in the recursive merge sort is divide. Okay? So it is further divided into 4 lists. And then divide them again. Finally, every list has only one key. It means it is already sorted. Then it's time to combine, merge them. Merge, merge, and merge. Then merge sort is done. This page shows you the pseudocode for merge sort. Look at this page and understand the meaning of each line. Kim Jong-bin. Okay, what's the meaning of the first line? Line 1.
P means left. Index.
Okay, I will explain these parameters. A is the array. P is the starting index, and R is the last index. And the merge sort elements in the subarray from P to R. Okay, then what's the meaning of the first line of the pseudocode? Can you explain a case that the if sentence is not satisfied? 손광호.
Execute merge sort if the length of array is positive.
The length of array
Is positive.
is
Positive.
positive.
It's like P is before the R, like 2 and 3.
So I mean, when the if sentence isn't satisfied.
4 and
2.
2. 4 and P is 4 and R is
But that doesn't occur. That won't occur. What is the exceptional case when the if statement isn't satisfied? If P equals R, it means there is only one key in the array. This part isn't performed because it is already sorted. So that's the only one case. It cannot be negative. Okay? So if there is only one key, the other lines are skipped and returned. Okay, then if the length is 2 or more, we perform the other lines. 박용호, 이동우. Okay, what is line number 2? Okay, compute the center element, Q, the index Q, right? And what are the lines 3 and 4? Okay, recursively call merge sort on each subarray. And finally, we merge them. So these are 4 main steps of merge sort. Okay, then let's measure the running time of merge sort. So this is the division step, and this is the conquer step, and this is the last combination step. But what's the running time of this? It takes constant time, okay? So it takes theta of 1 time. And then, how about this? Steps 4, 3, and 4. Let T of n denote the running time of the merge sort when the number of keys is n. Then the running time of this merge sort can be denoted by T of n over 2, because the size of array is halved. And there are 2 of them. We have 2 recursive calls, so the running time is doubled. Okay? So we so I explained up to the conquer step. And finally, the merge step. What's the running time of merge in this case? Okay, let's see. What is the running time of merge if the list of the number of keys in one list is n1 and the number of keys in the other list is n2? What was the running time? n1 plus n2, okay? Then in this case, what is n1? n over 2. What is n2? Then it's n. So the running time of merge is theta of n. Okay? So like this. So the running time of merge sort, T of n, can be represented as a recurrence like this. T of n is theta of 1 if n is 1. Otherwise, it is twice T of n over 2 plus theta of n, like this. This is a recurrence. To calculate the exact value of T of n, we have to solve this recurrence. And I show you how to solve this recurrence. First, we eliminate asymptotic notations. In this recurrence, there are 2 asymptotic notations, theta of 1 and theta of n. And we replace theta of 1 by a constant c, and theta of n by a constant multiplied by n, cn. Okay, then we solve this recurrence by using recursion trees like this. First, what's the purpose of this? The purpose is calculating T of n. Okay? Then look at this equation. T of n is a summation of 3 terms. Cn plus 2 T of n over 2. Okay? So this one can be replaced by these 3. And the summation of all terms in this 3 is the same as T of n. Okay? Then we do the same thing on T of n over 2. Look at this. This satisfies on every n, so we can replace n by n over 2. Then what's the value inside these parentheses? N over 4 plus, like this. Then we further replace this term by the right-hand side of this equation. Then we will get this. Okay? And we do this until we reach the bottom. Then we get this recursion tree. Look at this recurrence. When n is 1, it is C. Okay, so it's Cn, Cn over 2, Cn over 4. So if this is the same as n, then it becomes C. Okay, then now there is no T of something term in this recursion tree. So we can add all the terms in this recursion tree. Now let's add. But look at this. The summation of all terms in each level is Cn. Okay? 1 Cn, 2 Cn over 2, and 4 Cn over 4, like this. So the only remaining thing is to count the number of levels. And it is log n plus 1. So let's count the number of levels. This is level 0, and level 1, and level 2, level I. Then, in level 1, it is divided by 2. In level 2, it is divided by 2 squared. And then, in level I, it is divided by 2 to the I. So, we have to compute I. In the bottom level, this is the same as C. A simple calculation makes this like this, and by definition of log, I is log n whose base is 2. And log whose base is 2 is simplified by binary log LG. So the bottom level is log n. And because we started from level 0, there are log n plus 1 levels. So the total, we multiply Cn by log n plus 1, and then we get Cn log n plus Cn. And Cn log n is asymptotically bigger than n, which will be explained on Friday. So we can safely remove the linear term, and its asymptotic time complexity is theta of n log n. Any questions? If you have a question, raise your hand and ask me. Or I'll ask you. Do you know this all? Do you understand this completely? I don't think so. Okay, so I explained how to solve the recurrence of merge sort. And I will explain more general divide and conquer approach. The general divide and conquer approach is like this. The number of subproblems is not limited. There can be any number of subproblems. In this case, there are a number of subproblems. And each subproblem size is n over a. Okay? So if a is 7, there are 7 problems, and each subproblem has of size n over 7. It's possible. Even this is possible. The number of subproblems need not to be the same as the subproblem size. There are a subproblems, but each problem size is n over b. This is even possible in a general divide and conquer approach. But our merge sort case is the simplest case. What is the value of A of merge sort? 2. And what is the value of B of the merge sort? What is the value of B? It's 2. Look at this. A is 2 and B is 2. So in general case, we get this recurrence. Can you explain this recurrence? This is the division time and this is the combination time. So only focus on the first term. 박성현. Okay, explain the first term. Why it has this form. 윤호상. 이선민. 이치호. 조정환. Can you explain the first term? Why it has this form?
N over B is size of ID.
Mm-mm-mm.
And A is number of divided.
Sub-problems. Yes. Because, yes, the sub-problem size is n over b, so it is t of n over b. And there are a sub-problems, so a is multiplied by this. In the multi-sort case, a is 2, b is 2, so it is simplified like this. And the division time is constant, combination time is linear, so it is simplified like this. Okay, this is the revival of this. Okay, there are some self-study topics. Okay, then let's talk about binary search and selection sort. Do you know binary search? 최경련. Can you explain what binary search is? Okay, when you play a game to guess a number, for example, assume that I pick a number between number 1 and number 10. It's an integer. Then you guess a number. Then I'll tell you, I answer if in 3 ways. Your guess is right, or your guess is too big, or your guess is too small. Okay? Then what is your best guess for the first time? 9? 1? 5? Yes, 5. Then, what if I say it's too big? What's your next guess? 2 or 3? Okay? So, then the problem size is halved. Okay? That's binary search. Then, what's the running time of binary search? Let n is the range. Log n, theta of log n, y. Y Can you write a recurrence of binary search? The recurrence of binary search. T of n is, binary search is like this. It's not a divide and conquer approach, but you can write it as a recurrence. One guess takes constant time. I mean, comparing the guess and the hidden number. Okay? Then after the comparison, the problem size is halved. Okay? So you can get, and a simple calculation leads to theta of log n from this recurrence. And then selection sort. Have you ever heard of selection sort? 이규빈. 임민채. Selection sort. Hard to explain in English? 이명수. I can't hear you. Speak up. No idea? 임준수. 조윤아. I explained this in Java class. I remember that. 차정민. 김병준. 손혜성. No idea? Selection sort, there is a hidden word here. It's maximum selection or minimum selection. So let's say it's a maximum selection sort. There is an array. And first, we scan this array and find the maximum element. And let's say it's here. Then, swap this maximum element with the last element in the array. Okay? Then, we do the same thing with the array of size n-1. We scan this array and then find the second maximum element and swap it with this position. Then we can get a list, we can get a sorted list. It's selection sort. Then what is the running time of this selection sort? What is the running time for the first maximum selection? we need around n operations and comparisons. More exactly, n minus 1 comparisons plus 1 swap. So approximately n operations. And what's the next, what's the number of operations in the next round? N minus 1 operations, then n minus 2. Then what is the summation of this value? This. Then it is theta of n squared. And you can write the running time of selection sort as a recurrence. T of n equals what? Yes, T of n minus 1 plus theta of n. So this time is the time required to find the maximum element, and all the other rounds are incorporated into this time complexity. And this is an old version. And so a programming assignment will be announced sooner or later. I promise it will be announced by Friday. So, yeah. And it will be announced on our website. Any questions? No questions? You understand this all? Really? Okay, then I will ask you, Wang Jiamin. Okay, how many sorting algorithms did you learn in this course? Four. Oh, really? I taught three. I know I taught three, but what is the fourth one? Name one by one. What? Yes, selection sort. Merge sort. Binary search is not a sorting algorithm. It's a search algorithm. And finally, you don't remember what you've learned in the last lecture. 이문영. Yeah. What's the last one? Insertion sort, right. We learned 3 sorting algorithms: insertion sort, merge sort, and selection sort. So now you can program all of them. And 이희준, what is the running time of insertion sort? N minus 1? N minus 1. 임하경, what is the running time of insertion sort? N squared. Yes. It's N squared. But its worst case running time is theta n squared. But its running time is big O of n squared. There is a difference between theta and big O, and I will tell you on Friday. And 정구열. 정구열? 정구열. You just got up. What is the running time of selection sort? Pass. 조경재. Logan? Logan? 조경재. 조한방. Selection sort, running time. N squared? Yes, N squared. So, both insertion sort and selection sort run in N squared time in the worst case. How about the best case? What is the best case of insertion sort? 주정한. N, yes, theta over n, insertion sort. How about the selection sort? 현은율. What's the best case running time of selection sort? N squared, right. There is no best case and no worst case for the selection sort, because we have to scan the whole array to find the maximum. But in the case of the insertion sort, the insertion process sometimes stops earlier or sometimes stops later. So there is a difference. How about the merge sort? 윤영주. What is the best case running time of the merge sort? Anna? Best case? No idea? Same? Okay, why? No difference. Yeah, the merge procedure doesn't depend on the key values. It performs merge mechanically. So no difference. No difference, Selection sort, no difference, but there is a difference in the case of insertion sort. And the final question is, I said the insertion sort is stable. Do you still remember that? I'm sure very few students still remember. So it's this. If only constant number of additional array is used, except the input array, it is called a stable sort. And we know that the insertion sort is stable. Okay? Then, is selection sort stable? Selection sort. Is it stable? Park Jong-hoon. Is it stable? 박근배, 김범진. It's stable. Yes. When we find the maximum element, we need just a few variables. It's done. Then, how about the merge sort? Is it stable? Stable? 장영민. Is it stable? I can't hear you. There is nothing on this page. You'll have to look at this page. Is merge sort stable? Yes? Unfortunately, it isn't stable. When we merge two sorted arrays, we need an additional array to store the output. So, it isn't stable. So, even though the merge sort is faster than the insertion sort, its memory requirement is higher than the insertion sort. So sometimes you cannot run merge sort because of the memory requirement. Okay. Then, any questions? Okay, then let's wrap up this class now and see you Friday. Bye.